All right, ladies and gentlemen, please give me your attention. Okay. This is called a glitter lamp. It's very similar to a lava lamp. Okay? And what I'm going to have you do in just a moment is I'm going to have you draw the glitter lamp. Okay, I'm going to have you draw it. And it's just like a rectangle on your paper, and I'm going to have you fill it with atoms. Because really, what's in here that has atoms?
The glitter.
The glitter, but what is the glitter in?
Water.
Okay, it's in a liquid. It's in a liquid. All right? And so we
What
have...
kind of liquid is it?
Good question. I don't know.
Is it denser
Okay.
than water?
Well, we'll have to talk about that, and we're going to come back to that idea of density, okay? So what we have here, ladies and gentlemen, is a glitter lamp. And what can you tell me is happening inside the glitter lamp? Yes?
The heat is causing the particles to move up because it's on the heater. The heat's causing the particles to like circulate through.
Okay, so the
Or
heat
it's-
is causing the particles to circulate.
Or it's kind of like the Wonder Sticks.
Okay, it's kind of like the Wonder Sticks, yeah, where the particles are moving around inside the liquid too. All right, well, can you at least tell me what kind of heat transfer is taking place where the glass is touching the hot plate? Okay, starts with a C. We talked about it last week. Starts with a C. Yeah.
Convection.
It's not convection. That's what we're going to talk about today. This, where the hot plate is touching the glitter lamp, what is the form of heat transfer? Yeah.
Conduction.
Conduction. Ladies and gentlemen, you need to write that idea down and star it. Contact, collisions of atoms, heat transfer through collision is conduction.
I got that.
Heat transfer through collisions is conduction. Now, I'm not going to go in great depth on this because there's like a 40-minute video online that explains this in great detail. But you do need to understand you will have to describe that idea for your test next week. So if you don't understand that idea, get it down. Now, like I said, I already did a 45-minute lesson on conduction and only conduction last week. So that you should have lots of notes on that. And you should have it. You should already have it down. Now,
no, we weren't supposed to
what
take
we
notes.
are,
You didn't have us take notes.
but you can print them off. What I want you to focus on today is this idea called convection. Okay, it's not the contact through collisions between the atoms that's happening at the hot plate I want you to be concerned with today. What I want you to be concerned with, and what I want you to really take a close look at, is what's happening above the hot plate. What's happening in here? Okay? What do we see happening? Emma hinted at it. Okay? Yeah.
Is it the fact that the heat are moving the atoms really, really fast and it's making the rest of it move around?
Okay, so
But
there's
it's all
heat
moving slow.
moving atoms. At the atomic level, they'd be very fast, and it's causing things to move around. Sure. Typically speaking, what's the general flow here? What do you think is happening? Jade?
It's kind of like the water cycle. Like when it gets really hot, it goes up. And
Okay, stop there, and I'm going to let you finish. When it gets really hot, it goes where? Jade? Up. Okay. And then up here, is it as hot?
No, it cools down and then it goes back.
Okay, it cools down. We're not just saying and cooling down means what? Because the object can't get colder. What's happening? Elizabeth?
It's losing its heat.
It's losing its heat, and it's losing its energy. So it gains what down here? Jackson?
I got a question.
Hang on a minute. It gains what near the bottom? Heat, energy, rises, loses energy, and then does what? Grace?
It starts sinking.
It starts to sink and fall. Absolutely. Question?
Well, what I was thinking was that the reason why the glittery things are moving is because when it's kind of like the water that's in it, it's making it move up, right?
Okay, it's making it move up, sure. Does it look like it's going in a cycle?
Yeah.
It does. Jackson, you had a question?
So, I don't know if it's kind of like relate, but say like when it's cold outside and you put like a hat on,
Yeah.
like a stocking cap or gloves on, is that like, because isn't that like keeping the heat in?
Yeah, but that's
Or is that-
conduction. That's conduction because it's touching your skin. Okay? This is the idea that heat is moving in a space. So I'll give you an example. Anytime there's contact, that's conduction. Atoms are hitting atoms. It's a collision. Okay? So when you put a hat on, heat is heating, your head is warm, so the particles are trying to hit the hat, but your hat doesn't absorb lots of energy because it's what? A conductor or an insulator? Your hat that you wear in the wintertime is what, Caleb?
Insulator.
It's an insulator. So it doesn't allow energy to move very freely. So the energy stays inside your body, and then hence you stay warm. That's conduction. Okay? Conductors, insulators, things like that. This is different. This is a space where heat is flowing around and around. We see that the material is kind of going through a cycle. It's rising and it's falling. Okay? Take a look over here. What's happening as the fluid gets closer to the bottom? What's happening as the fluid gets closer to the bottom? Yeah?
It starts, well, it kind of makes this little, like, jet, and then it kind of shoots up.
Okay, it kind of makes a little jet. It shoots up. So the material starts out near the bottom, and it gains what?
Energy.
It gains energy, heat energy, which means that the particles are moving faster or slower? Faster. Okay, and so then they get excited, they rise, the whole blob rises, and then it gets near the top, and what happens? Yeah.
It loses energy towards the top.
Loses energy towards the top, and
It starts to drop.
it starts to fall. Now the question is, and the real question that has to be answered today is, why does hot substances rise and cooler or less energetic substances fall?
Like they say, heat rises.
Heat rises, or hot air rises, cold air falls. But we know that, we've learned that, we've seen it happen, we use it in our homes to heat our food in the oven, to heat our homes with forced air. But, ladies and gentlemen, there's still no explanation why it works. Why does hot air rise? Why can't it sink? And that's what we're going to look at today. All right.
We do fill it with atoms.
You do fill it with atoms. Yep. Okay? And
Should they be close together?
you can make them kind of big. I'll show you my example of what we're talking about here. Okay? This is what I have. Okay? Be about the size of a postcard or a business card in my notes. And I'm going to go ahead and put atoms inside it here. It's going to take a little bit, so I'll do it while you're doing it.
Different colors?
You want the atoms to be the same color for now.
But can we make them a different color than the box, the square?
You could if you want, but we're going to actually be drawing over top of these atoms with a different color. So you're going to want to be careful what you do.
I mean,
Okay.
space in between them.
Just kind of model what I'm doing. Notice I've just drawn a simple box with circles in it. This is going to be our heat, this is going to be our glitter lamp, okay? And we're going to put it on a hot plate. Down near the bottom, like so. Okay, so we have our glitter lamp sitting on a hot plate, and we've got all these atoms inside it. Now, we know from what we've observed that the atoms inside are moving. They are. There's this upward or upwelling of fluid that's going up, and we know that that fluid is going up because it's warmer. We also know that there are some fluid that is going down because it is cooler, or it's lost energy. That's a great way of thinking about it. It doesn't get colder, it loses energy in the process of going up. So it goes up and loses energy and then falls. Okay? Now, I want to think about this in terms of floating and sinking. Okay? Floating and sinking. So on the one side, we have a group of atoms. We'll call this our little pocket of atoms. Okay, this is going to be a pocket of atoms. Okay, it's a little pocket of atoms. And we are going to say that there is going to be this floating effect that's taking place. Okay? Now, so it's going to start here at point A. and it's going to float upwards. And we're going to have to figure out why it does that. And then we know that this little pocket gets up here, okay, at point B, like so. And we know that it loses energy, okay? So at point B, we know there's a loss of energy. And then we know that as a result of that loss of energy, that pocket is going to sink back down, okay? And I'm just going to call this sinking effect point C, because it's the motion of the pocket sinking. Sinks back down. So we start with a pocket of atoms that gains energy. Floats, loses energy, sinks.
Oh, so that says sinks right there.
Yeah, sinks. I'm not talking about having multiple basins for washing dishes. Okay? I'm talking about actually sinking down, 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 down.
It sounded like the end of a song.
Okay. Now, the question is, why floats, why sinks? I want to pull away from this for just a moment. We're going to come back to it. It's better when we think of floating and sinking if we think of objects that float and sink in water. Okay? So, I'm going to go ahead and draw some water here for a moment. Okay, I'm going to draw some water. And on the surface of this water, I'm going to go ahead and put 2 cubes.
Should we draw the water?
You might want to. Okay, I'm going to draw 2 cubes. Like so. They're in water. Water is made up of what? If we really were to zoom way in, it has what?
H2O.
It has H2O molecules. Okay, so there's going to be little H2O molecules that these blocks are sitting in. Okay, and I haven't told you what the blocks are yet.
They look like ice cubes.
They kind of look like ice cubes, sure. Okay? So we have water. It's made up of molecules, H2O. H2O molecules actually kind of look like this. They've got little spherical ears. They kind of look like Mickey Mouse a little bit. Okay, kind of like that. H2O molecules, and we have a bunch of them. I'm going to tell you that this block right here, we're going to call is a solid chunk of metal. Okay, solid metal. And I'm going to tell you that this chunk of wood right here, this is something that sinks. Okay, we're going to look at a chunk of metal that sinks. And what is something that floats in water? Parker?
A rubber ducky.
A rubber ducky. Let's pick something that has the same composition throughout, but yes, rubber duckies do float.
I still have one.
I still have a rubber ducky as well. Okay, yes.
Wood.
Wood, okay? I'm going to go with that example. I really like that example. Wood does float, or at least most wood does, unless it's waterlogged. We're going to talk about a
My
fresh
brain sinks.
log of wood. Okay,
We should do brain.
so metal sinks and wood floats. The question is, why? What do you think? Parker?
Well, probably because metal, all the particles are together.
Oh, I like that. Close together?
Yeah.
Oh, yeah. Yeah. Mm-hmm.
He
I like
actually
that a lot.
thought of something good.
Oh, that was wonderful.
What?
Okay, so
I go to the next.
Parker, hang on.
Okay.
All of these particles are really, really, really close together. Okay? Is there a way we could describe that scientifically?
Dense.
Oh,
Solid.
oh man. Oh, whoo! Oh,
Solid.
yes.
Solid.
Dense. Very dense.
But wouldn't it be solid too? Because if the particles are close together, then it's a solid. Well, wood's a
Yep.
solid too, so it
Exactly.
doesn't matter.
Oh my gosh, I am so excited about this word dense is super
Are we doing
important.
better than the 8th graders?
Well, there's no better or worse.
You can't show
Each class is unique and different. Okay?
Our class
True.
is highly unique.
Okay. So what we're saying is, yes, the metal is very dense.
Can I go into the wood?
Hang on.
Okay.
Density, ladies and gentlemen,
Density causes things to sink.
is, or float, is the mass in a volume. Okay, what that means is it's the amount of mass per volume. Mass per volume. How much stuff is in a space? I'll even let you. How much stuff is in a space? This is density. Okay? Now, wood
Can I say mine?
Wood is unique. What do you think, Parker?
Well, because if you look at a metal, it's like there's no, like, in wood there's a little, like, this empty space.
Oh my gosh, Parker, that's just the most perfect statement ever. Okay? Yes, that's exactly it.
His
There's-
head's working.
There's little pockets,
Oh, it's never mind.
okay? Mostly because there's a lot of air in wood, and air is a gas, and gas particles are really spread apart. And what's between gas particles? Yeah.
Air. Empty
Okay,
space.
but let's even think about that. Air is gas particles, but there is
Because Democritus had the theory of empty space.
exactly.
Empty space theory.
There is, ladies and gentlemen, lots of empty space.
But you don't see it.
You don't see it.
Well, you can see a little bit because you see little cracks.
Okay, there's cracks, and then those cracks are air, but even between those air particles, there's empty space. There's a lot of empty space, a lot more empty space. Is there still empty space in the metal?
I can't see.
Yeah, there is. Between the atoms, there's still empty space, but there's a lot less of it. There's a lot more mass in a metal than there is in a wood. There's a lot more empty space in the wood. Okay? Look at the way I've drawn them. Would you say that the metal is more dense or less dense than the water?
Less dense.
Are they closer together or more spread apart than the water molecules? They're closer. So we would say that metals, or this particular metal, is more dense than water. What about the wood?
Less.
The wood would be less dense
So it floats. Like you.
than water.
I mean, I got empty space.
Okay. Now, I will tell you this, that water has a density that's equal to 1 gram per milliliter. Okay? Now, that's mass
Should
per
we write
volume.
that down?
You can. I'm telling you that you'll learn more about this in high school, but what I will tell you is that water density has a density, or is the density of 1. Okay? You'll learn more about what that number means later. So, you can tell me metals probably have a density greater than 1 or less than 1.
Great.
Yes? Yeah, don't be shy now.
Greater because it's more dense than water.
Okay, greater than 1. And the wood probably has a density
Less than.
less than 1. Okay? Less than 1. Okay. Now, what I want to draw your attention to, because now we're going to take it over, we're going to compare it to the glitter lamp, is that objects that are very dense, objects that are very dense sink, and objects that are less dense float. So, if I'm looking at the same pocket I'm looking at the same pocket of atoms here, moving inside the glitter lid. When these atoms gain energy, what happens to their movement? What happens to their movement? They go crazy. And as a result, based on the last couple of days of our notes, they do what? If they go faster, they move faster, they're going to do what? They're going to bump each other out. They're going to spread out. So these atoms are going to spread out, okay? And when they spread out, what happens to the density of this pocket of atoms? It gets less dense because there's now more what, Parker?
There's more space.
There's more
But
space.
then if there's more space, it'll go up.
Okay,
Because it floats.
that's exactly it. The pocket of atoms expands as it gains energy. And as it expands, it becomes less dense. And as a result, it floats. It floats. It spreads out and floats. As it goes to the top, there's going to be a loss of energy. What's going to happen to the movement of the atoms when they lose energy? Think about if you have a child that's coming off a sugar high. Are they going to move faster or slow down? They're going to slow down. And if these atoms slow down, are they going to continue to stay far apart?
Yeah.
They lose energy. Think of objects that drop in temperature. Do they spread out or do they shrink back together? They're coming together. They're coming together. So the particles are coming back together. Connor, are we losing empty space or are we going to gain it? If they're coming back together, we're going to lose empty space. And as a result, what's going to happen to the density when they get closer together?
Yeah.
Is that more dense or less dense?
More down.
More dense. So that's going up. More dense. More means an increase. So what happens, I'm going to recap this whole thing because we have just a little bit of time, okay? And then I'll take a few more questions. You have a pocket of atoms. As they heat up, they gain energy. And they start moving faster. And then because they move faster, they can go farther away. And they're spreading out.
And they're knocking others away.
And because they spread out, the distance from atom to atom is greater. And so there's more empty space between them. That lowers the density, just like the wood. Look at the distance between the atoms is greater. And wood floats. So because they're less dense, like wood, and everything around them is slightly more dense, it's going to float up through the liquid. Now, at the top, it's cooler. There's less energy. So the energy is sucked out of the pocket. And as a result, these fast-moving atoms, they slow down. And when they slow down, because they have less energy, and because they can't move as far, they get closer together. And as a result, there's now less empty space. They become more dense. And they shrink then. And when they shrink, they sink. So here's what we have happening. They expand, float, shrink, sink. Expand, float, shrink, sink. Expand, float, shrink, sink. Expand, float, shrink, and sink. This is convection.
I thought we were
Expand, float, shrink, sink.
Why is pool is only...
All right, ladies and gentlemen, last idea for the day. This one's a little bit more complex, okay? We have Michelle here. How do we heat? Michelle has to stay at a constant temperature. She has to stay warm,
Or she'll
okay?
die.
Notice I don't have a hot plate underneath here, okay? I'm not heating the air, per se, around her so that she is basically getting this nice convection oven effect. What I'm doing is I'm what? What do I have?
The sun.
What do I have inside the thing? Yeah. What's it called?
Heat lamps.
Okay. So I have this thing called a heat lamp.
How does it heat? If you go to Logan's, you can feel it.
kill
in the
Michelle.
doorway. You know what?
She'll be fine for a little bit.
Okay.
Look at her. She's like, what are
Okay.
you doing?
It's like, where'd it go?
It's a heat lamp.
I love looking all at bones.
All right, now,
Don't put it on my
if you were to come up and put your hand out here, you would feel heat. Some people even put these in their bathrooms in the ceiling so that it actually warms them when they get out of the shower and dries them off. Okay? Really comfortable, just so you know.
Also,
Okay.
really expensive.
Now,
I'm buying one of those.
this is a lot like the sun, right? Does the sun, is there anything between the sun and the earth?
Dark
Yeah.
Okay?
No,
There's Mercury, there's Venus, but is there anything between the sun and earth as far as atoms?
No.
There is nothing. There is literally nothing between the sun and earth. So you cannot have conduction, you cannot have convection, because both of those things require atoms, either through collision or through this expansion, expand, float, sink, shrink, or excuse me, expand, float, shrink, sink. Convection. So there's no collisions, conduction, and there's no expand, float, shrink, or sink, convection. So how does the sun get atomic bombs worth of energy to Earth every day?
Lizards die.
Yeah.
People die. Die by the second.
I guess the heat is like transferring.
I wonder if it hurts to lose energy. I mean, like lose heat from the, like it hurts.
Or maybe like the atoms in the sun are traveling to
Okay. That's what people used to think, that the atoms from the sun were traveling to Earth. But I'm going to tell you that nothing that's a part of the sun travels to Earth. That's a great hypothesis. Okay? That's a great hypothesis.
But if the, I guess I'm thinking about that now, like if that happened, then the sun would be losing density.
Right, then the sun would be losing density, and that's not happening. It's interesting. Yes, you want to go ahead?
Solar radiation.
Solar radiation. Okay, I want you to write this down. I'm not going to release you until you all have this written in your notes, and I can see it, because I see people packing up. I wouldn't do this if I didn't see people packing up. This is going to be your ticket out of here. Okay?
Solar radiation. How do you not have
Okay, solar radiation. I want you to write this down. The sun,
Wait,
Hold up.
the sun emits waves of energy that have no mass. The sun emits waves of pure energy that have no mass.
What?
It's pure energy.
Yeah, you heard it.
Think about it. Energy, what is it? As far as we know, it's massless. Okay? It's energy. And so the sun emits waves of energy. I'm not done. Waves of energy that have no mass. They are called electromagnetic waves. They're called electromagnetic waves. And the type that we relate to heat, like this lamp, which feels really good, by the way, it's called infrared.
Is that what they put at like fast food restaurants on food?
That's exactly what they do to keep the fries warm. Sure. This is producing massless energy. It's converting electrical energy into heat energy. There are waves traveling from this bulb outward, carrying energy. Now, listen. This is how it transfers the energy. When the waves hit an atom, what does the atom do?
Buzzes.
because it gets more energy.
It absorbs the energy, starts moving faster, its kinetic energy increases, and what happens to its temperature?
Increases.
It goes up. So it's literally absorbing this energy that's being radiated from the sun or from a lamp like this, and then its temperature increases. Michelle is heated by this. The energy is emitted by this bulb. It hits her skin. Her skin and her body absorb it. It heats up the air around it a little bit, but for the most part, most of the energy hits Michelle, and she absorbs a lot of it. This is not convection. This is not conduction. This is radiation. Now, not all radiation is infrared. There are different types. This is heat energy. We actually have satellites that can pick up heat energy, and we can see humans and animals and other objects that give off heat. Okay, like infrared cameras and video equipment and things like that. And the military uses this all the time because they can see inside buildings people that are warm or anything that is warm. It's like a thermal scope. What's that?
If you're freezing, and that would you not?
If you were in hypothermia, your whole body temperature drops, and so you wouldn't be giving off as much energy. Ladies and gentlemen, you are all giving off thermal radiation right now. You are all like this heat lamp. You all are giving off heat, and so you all are giving off radiation. Just like the hot plate over there, just like this lamp, just like our sun. So we have these three ways of heating something. We can do it through collisions, conduction, expand, float, shrink, sink, convection, or massless waves of energy called radiation.